Central sphere packing in a cube, a radial layer approach to asymptotic filling. Aaron Cattell. August 22, 2025. Abstract. We investigate a novel approach to sphere packing within a cube using a central expansion method. Starting with the largest possible inscribed sphere, we recursively add smaller spheres in radial layers, each tangent to previously placed spheres and constrained by the cube boundaries. This construction, analogous to Apollonian sphere packings, generates an infinite sequence of spheres with geometrically decreasing radii. We prove that while no finite configuration can completely fill the cube, the packing density approaches unity asymptotically as the number of spheres tends to infinity. This result demonstrates that a cube can be almost filled by countably many spheres through systematic radial expansion from its center. Introduction. The problem of efficiently packing spheres within geometric containers has fascinated mathematicians for centuries, with applications ranging from crystallography to optimization theory. The classical question of inscribing a single sphere within a cube has a trivial solution: a sphere of radius a2 centered at the cube's center, where a is the side length of the cube. However, more intricate questions arise when we consider multiple spheres of varying sizes. Traditional sphere packing problems often focus on identical spheres arranged in regular patterns, such as the face-centered cubic (FCC) or hexagonal close packing (HCP) arrangements. In contrast, this work explores a fundamentally different approach: a central expansion packing where spheres are added in successive radial layers outward from the cube's center. This construction bears resemblance to Apollonian sphere packings, which recursively fill spaces with mutually tangent spheres of decreasing size. Our approach adapts this concept to the constrained environment of a cube, creating a systematic method for achieving high packing densities through infinite subdivision. Mathematical framework. 2.1 Setup and constraints. Consider a cube Q equals 0, A3 with side length A. Let C equals A2, A2, A2 denote the center of the cube. We construct a sequence of spheres Sk or infinity. K equals 0, where each sphere Sk has radius Rk and center Ck. The constraints for our packing are: 1. Rk, 0 for all k greater than or equal to 0. 1. 2. Each sphere must be contained within the cube. Rk less than or equal to xk less than or equal to Ark. Rk less than or equal to yk less than or equal to Ark. Rk less than or equal to zk less than or equal to Ark. Where ck equals xk, yk, zk. 3. Non-overlapping condition: Cij greater than or equal to Ri plus Rj for I equals j. 2.2 Initial configuration. The construction begins with the largest possible inscribed sphere. S0, R0 equals A2. C0 equals C equals A. 2, A2, A2. 1, 2, 3, 4, 5. This central sphere S0 is tangent to all 6 faces of the cube, establishing the foundation for subsequent layers. Radial layer construction. 3.1 Layer generation algorithm. The radial layer construction proceeds through the following recursive process. Layer 1, place spheres Si tangent to the central sphere S0. For a sphere with radius R1 in this layer, the center must satisfy C1C equals R0 plus, R1 equals A2 plus R1. Layer K, 4K greater than or equal to 2 new spheres are positioned to be 1. Tangent to at least one sphere from a previous layer. 2. Tangent to cube faces when geometrically feasible. 3. Non-overlapping with all existing spheres. 3.2 Geometric constraints and radius determination. 6. For spheres in layer K, the radius Rk is determined by the available space between existing spheres and cube boundaries. The geometric constraints create a system of equations that can be solved to find optimal sphere sizes and positions. Consider a sphere Sk positioned to be tangent to sphere Sj, where j less than k, and constrained by the cube boundary. The radius Rk is bounded by Rk less than or equal to mina 2 d face Cj/Ck 2 Rj, where d face is the distance from the prospective center to the nearest cube face. 7. 2. For analysis of packing density 4.1 density definition, the packing density for n spheres is defined as n equals n1k equals 0.43 r3k, a3, 8. 4.2 Asymptotic behavior. The radii Rk a form a geometrical decreasing sequence, and the packing density approaches unity as the number of spheres approaches infinity. Their recursive nature of the construction ensures that available space E decreases geometrically with each layer. Specifically, the radius of spheres in layer X satisfies Rk times k, 9, 4 semiconstants, 0 and 0, beta, 1. The infinitesium of sphere volume S converges. Infinity k equals 0.43 r3k equals 433 infinity k equals 0.3k equals 433, 13, 10. As the construction fills increasingly small gaps, the total volume E approaches to cube volume A3, yielding lim infinity n equals 111. 5 Geometric visualizations S0 AA S1 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 Figure 1. Cross-section view of the central sphere packing, showing the central spheres 0 and 4 first-layer spheres. The construction maintains tangent-psi conditions while respecting cube boundaries. 3. Figure 2. Three-dimensional visualization of the central sphere packing showing the central sphere, blue, first-layer spheres, red, and second-layer spheres, green. The recursive nature of the construction is evident in the decreasing sphere sizes. Computational aspects. 6.1 Algorithmic implementation. The construction can be implemented algorithmically through iterative optimization. 1. Initialize with the central sphere S0. 2. For each layer K. A. Identify potential sphere positions using geometric constraints. B. Optimize sphere radii subject to tangency and containment conditions. C. Add spheres that satisfy minimum radius thresholds. 3. Repeat until desired precision or maximum iteration count. 6.2 Convergence rate. The convergence to asymptotic density follows a geometric progression. For practical implementations, achieving density ρ greater than 0.95 typically requires O log 1 layers, where epsilon equals 1 ρ is the desired accuracy. Comparison with classical packings. Unlike regular sphere packings that achieve specific density values, e.g., FCC packing with ρ equals pi 3 square root 2, almost equal to 0.74, our central expansion approach theoretically achieves unit density through infinite subdivision. This represents a fundamentally different paradigm in sphere packing theory. The trade-off lies in the requirement for infinite spheres versus finite configurations. While classical packings provide finite solutions with known densities, our approach offers asymptotic completeness at the cost of infinite complexity. 4. Extensions and applications. 8.1 Higher dimensions. The central expansion principle extends naturally to hypercubes in Rhode. The central hypersphere has radius A2, and subsequent layers follow analogous tangency conditions adapted to higher dimensional geometry. 8.2 Non-cubic containers. Similar constructions can be developed for other convex containers, including rectangular parallelepipeds, spheres, and regular polytopes. The key requirement is the existence of a well-defined center and systematic layer-by-layer expansion. 8.3 Physical applications. This packing approach has potential applications in material science, modeling particle arrangements in constrained geometries, computer graphics, procedural generation of particle systems, optimization, space-filling algorithms for resource allocation. Conclusion. We have presented a novel approach to sphere packing within a cube using central expansion and radial layer construction. The key findings of this work include 1. Systematic construction. The radial layer method provides a deterministic algorithm for generating dense sphere packings from the center outward. 2. Asymptotic completeness. While no finite configuration can completely fill a cube, our construction achieves unit density in the infinite limit, demonstrating that cubes can be almost filled by countably many spheres. 3. Geometric convergence. The sphere radii decrease geometrically, ensuring convergence of the infinite series and practical computability of high-density approximations. 4. Theoretical significance. This work bridges classical sphere packing theory with modern concepts from fractal geometry and infinite subdivision processes. The central expansion approach represents a departure from traditional uniform sphere packings, instead embracing the concept of hierarchical space filling through infinite subdivision. This paradigm shift opens new avenues for research in computational geometry, optimization theory, and applications requiring efficient space utilization. Future work could explore optimal ordering of sphere placement within each layer, extension to non-convex containers, and hybrid approaches combining central expansion with classical packing methods for specific density targets. The mathematical elegance of achieving asymptotic unit density through systematic radial expansion demonstrates the rich geometric structure underlying constrained sphere packing problems, and provides a foundation for further theoretical and practical developments in this classical field. 5.